I'm gonna do that.
So
That's
there's
it.
one,
That's
like,
the next prank.
She basically said everything that's in the real article.
That's what she did with the one that I did too. She just took like all the understandable stuff.
Right, that's
And put it
that's
in-
the whole point of
Yeah.
the thing, is to take an article and condense it down into
'Cause I
something
looked
that's
at the other one.
No,
understandable.
but like the real scientific
Yeah.
article didn't have any like more layers really.
Okay, that's
It was just
good.
like what she said, and then they just said the same thing, except they didn't really explain it. So I guess it's just like a PhD.
Right. Those who will be reading the article professionally don't need to.
Yeah.
Okay.
Okay.
Oh, what happened?
Thank you. I got it at Goodwill.
Along with one of them, one movie.
Yeah, Goodwill movie.
Okay, you're good to go. You're fine. I'm movable.
Hello, my name is Liam McDaniel. That's Betelgeuse, and it is set to go critical within the next 100,000 years. So astronomers have been staring at it for a while.
But it could be tomorrow.
It could be tomorrow, within the next 100,000 years. You know, so it could be right now. We just wouldn't know. Basically, in early 2020, there was this weird thing that happened to where the magnitude of the brightness of Betelgeuse went from 0.5 to 1.5, which is one difference, but as we know, it's 10 times less bright. So, and it was actually so much so that it was observable to the naked eye. Like these are taken like 6 months apart, these images. So if you looked up, you'd be like, what, how come it's fading? And basically there's 3 different possible explanations that were proposed that I saw at least. First one was that something just got in the way. There's interstellar dust going between us and Betelgeuse. That was like the most obvious and basic one. Maybe something's blocking it. The second one is that there's a variation in the convective cells, which basically would just mean that, like, based on the way the convection currents are happening, it's just a cold spot, and it's just a temporary coldening. That's not a word, but cooling. That's the word I'm looking for. And then the third reason is the critical translation in the pulsation dynamics of the star. Now that's a lot of syllables, but basically what it means is that the base, how the star functions and the inside dynamics of it are changing from one stage to another. That's basically saying that it's transitioning from whatever phase it was in to even closer to the critical stage, in which it should be going supernova soon, based on our models, and also based on its size and where it is. It's already past the main sequence. Now, this is the first idea, was that it's interstellar dust going between us and Betelgeuse. The idea, but the reason why this got shot down is because if we did see that, do that again. As the dust got in the way, the wavelength, like arcs, the wavelength profile should be like condensed and also brought towards more infrared based on the light going through interstellar dust, as we've calculated things like that before. However, we've seen no evidence of the wavelength profile changing that dramatically. So that's why we can kind of chalk up that idea and kind of eliminate that possibility. Another possibility was the convection cells, for the temporary cold spot. Now in the red, we have the wavelength profile from 2004 versus this weird function. And in the black, we have it in 2020 during the dimming event. And based on these differences and how they fit the models, they pair it to the models based on different temperatures. And they found that the only difference, the temperature difference between the two was about 50 Kelvin. So it could not have resulted in such a difference in the brightness. So basically what this is saying is that the temperature was only about 50 Kelvin different, with a maximum of 100 Kelvin different, with a minimum of 0. So it's like anywhere between 0 and 100 Kelvin different is not enough to justify that change in brightness. So that's why we kind of chalk up this solution. And this was done by a different paper. And then this is the final one, basically what the paper is about, the critical transition and the pulsation dynamics of the star. And the way that they're able to tell this is by 3 quantifiers that are used as early warnings of system change. And these quantifiers are derived basically through various measurements. And that's the lag1 autocorrelation, which is this first one on the left. The middle one is the variance, and the right is the Hurst exponent. If we see, right, this is before 2020 and then during the 2020 dimming event is what it's called. We see this trend upwards. This is from, green is from 1990 on, and the gray is from 1984. So basically, what they're figuring out here is that there was like this buildup and then this drop off during the dimming event, which could be used to create these 2 graphs, which is the determinism and the laminarcity. Not laminar. I don't know. Laminarcity. I don't know if that's the right word. I don't know. But the point is that before the dimming events, these 2 qualities built up in the star, and then during the dimming events, they dropped off, indicating a change in like cycle, a change in the dynamics on the inside of stars. And that's pretty much what it was all about. It's just that the results are mixed. We know it's probably not dust, and it's probably not just the thing cooling. So they got those derived qualities, and they realized that there was this buildup and then this drop off during the dimming, which represents like almost like a jump to a different phase in the star cycle, which means it's getting closer and closer to going critical every day. And that's it. Any questions? Yeah.
So, your article talks about this being a critical point in a phase transition. Did they mention did they talk about like a comparison between the before phase and after phase for the transition, like what that looks like? Like, is it just like all the currents are rearranging themselves?
Yeah, basically it's less to do with the emitted wavelength and the temperature, obviously, but more to do with the internal dynamics of the star and what's changing. It didn't break down which phase, say whether it didn't say, well, it's working its way to iron. It didn't say anything like that. It was just going on about how it's burning through and it's changing how it's burning on the inside based on these early warning quantifiers. If that answered your question at all. Yep.
Just looking at the third graph, would it be right to say that it kind of proves that the RF cycle, because there's at least 2, if not more, other bits that have occurred in Betelgeuse?
You're talking about in the 1980s, like in the before?
Yeah, just looking at the very end of the green, it's definitely getting low, but then it spikes up and then it still comes back down.
Well, they said that this time the cycle is different. I think these graphs, they don't have all the dimming data included, but if you look here, these are more, it's more clear to see because these are like parts of the functions to make these. So basically before 1990, it was pretty consistent, and then in the last 20 years or so, it built up. And that's basically what they're referring to in that, yeah, there's some type of cycle, obviously, but the cycle's at a different phase now, like it's completely changed in the last 2 years, year and a half.
It isn't really a question, but I would be curious to know if you had input at, and like, I looked into Betelgeuse like last year, and so like when it does go supernova, it's going to be and the brightness of the full moon, like at night, and it's going to be visible during the day. So was there anything else in the article that talked about what would happen when it goes critical?
No, it didn't really go into how much what's going to happen as it goes critical. It's just saying that it's working its way closer to critical, and this is exciting. I think that would be a different thing, like what's supposed to happen. They're saying that they're waiting on for it to become more easily observable again, because I think it's not that observable based on what the article said at the moment. So, yeah, that's exciting if it got really bright and visible during the day. But this article didn't go into that. It just was going into the changes as it goes into going critical.
Did you show an actual light curve at some point?
The actual light curve. Yeah, this one kind of is
That's a spectrum.
yeah. This is I did. It didn't show the light curve.
Brightness as a function of time.
Oh no, it didn't show that.
So I'm wondering if the fatal juice is a variable stuff, right? It's doing stuff.
Yeah.
But what I don't know is how unusual this episode was compared to other dimming and or brightening events that have.
I can pull. I have that light curve that you were describing. I just didn't put it in this, which now I realize I should have. But it did spike and drop off dramatically based on where it was. It got dramatically less bright than the deepest divot, if that makes sense. It just looked like a squiggle and then a up and then a dramatic drop off, which was
And it's come back up now, right?
Yeah.
Back to where we started.
and then it jumped back up again. So basically, the amplitude of it changed incredibly, and if you were basing like a sine wave, the middle point changed as well. So that's why it's changing in the pulsation dynamics. They just decided to word it hard.
Oh, you have a PhD, it's could be used for this.
Yeah,
We have all that.
you got to prove that you know words.
Dr. Fennell, that random graph that you mentioned, would that be like the change in flux for whatever particles or energy that you're referring to?
I've never heard the word dynamistic. I have no idea what it means.
Yeah, I tried to find definitions on what they were talking about, but it was hard to find because anytime you look up, this one it said is determinism and laminicity. And I tried to find determinism, like what it meant in other contexts, and I could not find it because anytime you look up determinism, astrophysics, astrology comes up.
Yeah.
So
Can you bring up the slide that's got your three parameters though? Because I didn't understand lag one autocorrelation.
that was just one of the parameters that they
Yeah.
used.
Which is fair enough. So autocorrelation is, you can stand on that. So, it's kind of a cool thing. If you've got some periodic system or something that's doing things, autocorrelation is so so you can take two things and correlate with them with each other, and if they, you'll get a high mark if it's well correlated and they're doing the same thing, and you get a low mark if they're doing different things. Autocorrelation is correlating to itself. So take your time series, shift it by a little bit, and see if it's doing the same thing now as it was earlier. And so if things are really changing, if things are the same, then you'll get a nice strong correlation with itself. If things are changing a lot, then you'll get an autocorrelation that goes weird. And so I guess that's what you're seeing is were changes even before the dimming that led them to believe that things were happening here. The variance probably is just how much it's moving up and down as a function of time. And I have no idea what a Hurst exponent alpha is, so I'm gonna stop there. Okay, excellent. What else to do today before we get to this stuff? Yes, thank you. Look at that, it's the full moon in pink flowers. Pink, I guess, all the moons, all the full moons have names throughout the course of the year. I guess we just passed the pink moon. The next one's the flower moon. And I guess we're pretty close to perigee on the moon's orbit. So it's bigger, like 5 to 10% bigger than it is when it's at apogee. So. It's a small effect, so you'll see it. I mean, it's not a big effect. It's if you see them side by side, you can tell the difference, but it's hard to tell with the naked eye. It could have been probably. It always looks bigger when it's closer to the horizon, and that's a much bigger optical illusion than the actual bigger and smaller effect. But it's a real effect in that it's important because for eclipses, when the moon's close to us, it can cover up the entire solar disk. And when it's farthest away from us, it cannot completely cover up the solar disk. And so sometimes you get annular eclipses where the moon passes directly in front of the sun, but you still got a ring of it poking out because it's further away and it's not quite big enough to cover the whole disk. Fortunately, April 8th, 2024 is going to be April. It's going to be a near full, it's going to be near in its orbit. It must be because we got a nice total eclipse in Geneseo for 3+ minutes. It's going to be exciting. Come back. You're all invited. April 8th, 2024. It was a picture of the crescent Earth, not taken by Michael Collins, but Michael Collins being one of only 24 people, humans in the world, humans ever, who have been able to see this view, meaning the Earth as seen from a far enough vantage point that you can actually see the entire disk in one shot. And so,
the lands are going down.
Yeah.
To the moon with the Earth behind it, and
Yeah.
it's like pictured all of humanity except Nobel.
That's right. Who died at age 90 yesterday, and yeah, there's a Michael Collins remembrance thing here. Yep. So this was not taken by Michael Collins. This is Apollo 17. Collins was in Apollo 11. That was the first moon landing. So, yep. This is the last time. This is in 1972. December was the last time. This is on the way back that anybody had this view. It's been. I was born in 1974. It's not been in my lifetime even that anybody has been beyond near Earth. It's kind of sad, but maybe that'll change in the next decade. We'll see. The moon. Yeah. Well, we'll see if that happens. They were supposed to launch the Spitzer, the James Webb Space Telescope also like a decade ago. So I'll believe when I see it. I'm hopeful, but we'll see. All right. Pup date. I've got a special pup date today. Where'd it go? Right. So they're always sleeping this time. So we filmed them yesterday during the puppy stampede, where about twice a day we'll let them out of the pen and then they'll go crazy for 20 minutes or so. So here we go. The puppy stampede yesterday. This is probably the puppy stampede 2 actually. Okay. So Bailey, Hannah, puppy pen, get ready for pandemonium. Normally they just come running out. It was kind of a muted stampede this time, but they definitely are going to be running around like crazy dogs. Snoopy's going to come by in a minute. He's my, and you're going to see Mom, Nala, and Snoopy, who is completely freaked out by all of these puppies, runs by at some point, like, get me the heck out of here. There went Snoopy. There's Nala. And the puppies are everywhere. So it's pretty much pandemonium for 20 minutes, and they're like 7 toddlers let loose in your house. They're chewing on everything. They're pooping everywhere. They're biting on your ankles, and you're kicking them and tripping over them. It's complete joyful pandemonium chaos for 20 minutes. So we'll probably not this weekend, maybe next weekend we'll get them out sometime. I'll send an email out and you can stop by and you can pet the puppies. The ringworm's getting better. Won't be completely gone, but it's definitely improving. We got external medicine now and internal medicine. And, yeah, okay, there. All right, so that's fun. Weather? What? What? Okay, great. So where were we? Right, I was totally, so apologies for this. I totally messed this up yesterday. I don't know what's happening Wednesday. I was out of it. I was saying some stuff that none of it was right. It was, you know, we all have bad days. I had a bad day. So let me try to come back and set the record straight on how the elements are formed. So we talked about R process and S process. Those are things. They are both neutron capsules. Once you get to these high Z elements, it's really, really impossible to bang another proton in it. You just can't do it anymore. So we're always talking about adding neutrons. We're always talking about, in this graph, moving to the right, adding neutrons to our elements. This is fast. This is slow. That's basically the difference. One of them has to happen very quickly, and one of them has to happen very slowly. And so this one has to happen in supernovae, because that's where you're banging neutrons into things really fast. And this is not happening in supernovae. So let's try to again look at this diagram and figure out what the colors are and what's actually happening. So remember, the R process is you've got a heavy nucleus and you just bang it with neutron after neutron after neutron. What's going to happen? You're going to take an element that's down here and you're just going to move it way to the right. It's like you're shooting bullets at it, and the atom is absorbing those bullets, and it's just adding neutron after neutron after neutron, and you make these high N elements. They will eventually decay. Wherever you stop, they will eventually beta decay in this direction, wherever you stop. And so these guys are our process only because there are some, not, again, to get to this point, so this is maybe a stable isotope here, right? But this is a fairly slow, this is an unstable isotope, but it takes a while for that decay to happen. So the only way to get to that point is either to start here and add neutrons, and once you get there, you can stop, or to make any other lower element, a lower Z element, add a bunch of neutrons to it, and then just let it decay to that point. Right? But these stable isotopes provide shields that make it impossible to get to this element, for instance, by add a whole bunch of neutrons and then decay back in this direction. It's like a shadow. Each of these stable isotopes has a shadow. It's impossible to get to that point. You can only get to that point by these slower processes. And if the decay rate of this and this and this is stable. The decay rate of this and this are much longer than, say, the time that it takes a supernova to go off, then you can't get there at all by the R process. You have to go through some process where you add a neutron and then wait a while and let it beta decay. And then add another neutron and wait a while and let it beta decay. That has to be an S process. You can get to this with the S process too, but you can also get to this with the R process by making this element down here and just letting it beta decay all the way. So some of these most of these can be produced by the R process, but there are specific isotopes, which is interesting, that can only be produced in the other one because of the time periods of these. The beta decay is basically how unstable is it. Okay. So, sorry about that. Hopefully this cleared it up. That's basically the difference between R and S process. So this happened in supernovae. Where does this happen? This can happen in AGB stars. Remember, AGB are asymptotic giant branch stars. Let's just review our HR diagram here. Right, you got a low mass star, red giant branch, comes down here to some horizontal branch. And then the AGB is the, so again, burning hydrogen in a shell, burning helium in the core, burning helium in a shell are the AGB stars. So these are post-horizontal branch stars that are moving back up the sort of an asymptotic to the red giant branch track, right? And red giant stars too. But this seems to be, the star gets a little bit bigger here, and it seems to be like this is the place where this kind of thing will happen more. So the question is, we know where the neutrons come from here. Where are the neutrons coming from here, right? Neutrons have a half-life of about 11 minutes. You're not, unless you're creating them, they're not going to be around to do these reactions. So where are the neutrons coming from? Where do neutrons come from? And I'm particularly talking about in the S process. Well, it turns out that if you are doing, let's say, carbon burning, oh no, this isn't even carbon burning. This would be like a star where you're doing some horizontal branch or AGB stuff, because you take the carbon-13 and you can smash it with. So this is again not the most normal isotope of carbon, but it's not a really unusual isotope of carbon either. Smash it with a helium nucleus, you can get oxygen-16 is the preferred ending point for this reaction. And the other reaction product is actually a neutron. So if you're doing this reaction in the core, then you've got 11 minutes of that neutron where it can do some damage to something else before it decays into a proton, on average. And so then here's another example of a reaction where you can do this. Neon 22, which has, this is the 10, atomic number 10, again, plus He4, goes to magnesium 12. This is just a couple of the reactions that can happen to give you a neutron. And once you've got a neutron, again, this is happening at the centers of AGB stars, so it's really hot. These neutrons are moving around really fast. They can bang into an element and add a neutron to it. And it's probably going to be a while before another neutron comes along because these are fairly rare reactions. And then it can follow the S process. This is the example of how this can happen in a slow way, gradually building them up one neutron at a time over millions of years instead of seconds. Okay. Great. And I think P only in this diagram, you can only get to this, right? You can't, the S or the R process cannot get you to this interestingly stable, also stable isotope, right? This has to be a proton capture. The only way to get to this point is proton capture. You have to move up on this diagram. You can't get there by moving to the right. So, and the amazing thing is that 1957 paper detailed all of this stuff. They came up with pretty much from scratch all of this mechanisms and coined all of these terms for making these things. Let's go back and think about this one. Right. So the brown color is the R process elements. The green color, I think, are the S process elements. Some of them have isotopes where you get both S process and R process isotopes, depending on how many neutrons there are. Some of them are looking good. Oh, orange. It's showing up redder here than it is. I'm thinking about the one that says supernova.
Oh,
These guys.
I was like, wow.
Right. The small stars are, the CNO, not even CNO cycle. You're talking about synthesis in the center of the stars. And then hydrogen and helium are the only Big Bang ones. And lithium really weren't weirdos anymore. They're a class of their own. So there you go. We understand pretty much where all of the elements come from. Yeah, they're the weirdos.
So why does it suddenly stop? Like, why is there such a hard stop between the supernovae and the nebulae? Why can't supernovae make nebulae?
Right. They can, but these are not occurring naturally in nature because none of them are, there are no stabilized states. This is the hard stop this is the heaviest element that has a stabilizer. And so it might get made, but you're not going to see it in a star or in nature because it's going to immediately decay into something else. But, so we can make it in the lab, and we've seen it in the lab, but those are not naturally occurring. Yeah, probably. They just don't last very long, and they don't stick around long enough that there are enough of them that we can measure. Okay. Cool. All right. I feel better about that. I think we've played better. All right. By the way, who's on Astrobyte for next week? It's Bisma. It is on Friday, and Bailey, you're doing Wednesday. Okay. All right. Let's talk about the degenerates. We're going to start with white dwarfs. I like Bob because Bob always begins a chapter with some history. And so I like to begin these unit changes with some history as well, because it's kind of fascinating. The history of astronomy really is the history of science. You go way back, and we're stuck with so much of the structure that was built before we even understood what stars were or galaxies were, that it's useful to understand what that history is, to understand the structure that we're living within and are confined to, at least in our terminology. So 1838. There's a guy by the name of Friedrich Bessel, and he is famous because he was the very first person to measure stellar parallax. The Greeks knew that if the Earth was really moving around the sun, we should see stellar parallax, and they looked for it and they couldn't see it because the stars are so far away that their motions are so small. It wasn't until 1838 that anybody was able to measure this, which is pretty amazing in its own right. I think, and I have no idea how he did it. Photography isn't yet a thing then. It's like 1850s, I know it's around. I don't know if it's around in the 1830s yet. But maybe it is correspond with the very first photographic emulsion things where they could actually, because that's what you really need to do, right? You need to see where it is now, and you need to see where it is 6 months later. That's really hard to do with your eye, right? You have to really measure accurate positions and distances between things. It's much easier to take a picture now, take a picture 6 months from now, put them together side by side and see what the differences are in motion. Anyway. Oh, thank you, Google. So probably this was correspond, when new breakthroughs happen, when new technology comes along. And the new technology in 1838 was photographs. There we go. So there you go, 1830s. Photographs right there. Anyway, he measured it to 1661 Cygni, parallax of 61 Cygni. Friedrich Bessel. Friedrich Bessel. Probably not, but I have no idea. Sorry? It's a pot, yeah. It's a typical symbol for parallax, actually. It's pot. 61 Cygni. And, you know, the 0.286. I mean, you probably didn't measure that accurately. Again, it's a whatever large for which parallax was discovered and measured was Sirius. Sirius being the brightest star in the sky. And it's not even really close. It's like 2 times brighter than the next brightest star in the sky. Something like that. And its parallax angle, I'll call Q now, because why not communication hypothesis, 0.379, even bigger than 6160. The largest parallax angle is Alpha Centauri, or Proxima Centauri, and it's in the 0.4 range. Maybe it's 0.7. That's actually very good. So 0.7. Anyway, that doesn't really matter. So as they try, so they were finally, again, you're finally able to take photographs of things. You're finally able to measure the positions of these things really carefully. And Sirius has some proper motions. All of these nearby stars are moving through the sky at some slow rate. They were able to finally trace the motion of Sirius across the sky. And they noticed that it wasn't following a straight path. It was following kind of a sinusoidal path. It was the very first astrometric binary system. They could not see the binary companion. It seemed to be a single star, and yet it was making this wobble across the sky. The only explanation is it's in a binary system with something else that we can't see. So it was predicted to be there, but until 1846, nobody had seen it, nobody could see it, right? So fast forward, 1846, a new 18-inch telescope was built, very exciting, best of its time. And they looked at Sirius, because what do you do but look at the brightest thing in the sky with your new big telescope? And voila, there was the thing that they had been searching, right where they expected it to be. Sirius B. So now Sirius is a binary system. You've got Sirius A, which is the bright thing. And you got Sirius B, which is a different thing. Now, the luminosity ratio here was stunning. Something like 1,000 times. The luminosity of the brighter one was 1,000 times the luminosity of the bigger one. Right? This was a very large thing. We were able to, you know, Sirius is a famous star. We were able to measure its mass at about 2.3 solar masses. And, well, you can do the astrometric solution. Once you have both orbits, you can watch them go. You can get the relative masses. You know that mass B is on the order of 1.0 solar masses. Okay, so it's actually a fairly wide orbit, fairly elliptical orbit. The next time they got to be at their farthest part, at Astron, they're far enough apart that you can actually take spectra of each of them and get temperatures. And so measure temperature. And they were expecting, right, you got a 1 solar mass star and a 2.3 solar mass star. It's not surprising this one's a lot more luminous. 1,000 maybe is a little bit more than you would expect. But you would expect this one to be the hot one and that one to be the cool one. That's what they were expecting to find. They did not find that. The temperature of A was about 91, 99. And again, this is an A star. This is an A0 star, basically. And TB, which they were expecting to be smaller, 27,000 Kelvin. Highly unexpected. Totally blew out of the water anything that they had thought about stars and how they work. So you can make some, if you know the mass, you know the temperature, sorry, you don't know the mass. You know the luminosities, and you know the temperatures, you can derive the radii. This is a simple calculation that my stars and galaxies students could perform. So they can do that. We know that r squared is proportional to L over 2 to the 4th. This implies that RA over RB, and plugging in this number and these two numbers, has to be 234. The radius of the brighter object is more than 200 times that of the smaller object, of the dimmer object. This is more than the ratio between the Earth and the Sun. The Sun is about a little over 100 times the diameter of the Earth. These guys have a difference of more than a factor of 2, that difference. So we can, based on some luminosity and temperature arguments, actually get what these radii are. The radius of B has to be about 0.008 Earth radii. Oh, sorry, solar radii. Solar radii. For comparison, the radius of the Earth is about 0.0909 solar radii. This thing is just a little bit smaller than the Earth. It has to be. Even with measurements that they were able to make in 1840s, they knew that this had to be. And we know that the mass of this thing is about a solar mass from the orbital dynamics. So you've got an entire solar mass worth of stuff squished down into something about the size of it. What is the density of such a thing? It's astronomical. I had to wait for the right moment, and it just was there. I took it. Right, density is mass divided by volume, at least average density. We've got one solar mass here, basically divided by the Earth's 4/3 pi, pi times our Earth cubed. Plug all that in. Yeah, let's use Wolfram alpha. It's kind of fun to see these numbers come on. Because the thing I like about Wolfram alpha is it gives you comparisons. It gives you some, oh yeah, that's a big density. What's it comparable to? Let's just do it. It's pretty close. Yeah, I mean, these are all approximately equals to anyway. So order of magnitude, this is gonna be good enough. Yep. I do too. It's great. Okay, so you can even do this. Mass of Sun divided by volume of Earth. You can probably just do this. Boom, it's a density. Kilograms per cubic meter, oh yeah, 10 to the 9. 10 to the 9. So a cubic meter is a big thing, right? That's going to be this by this by this. But 10 to the 9 is a lot of kilograms. That's a billion kilograms. A cubic centimeter, well, let's just write that number down and think about it. About 2 times 10 to the 9 kilograms per cubic meter. Yeah, 2 times 10 to the 3, that's right. kilograms per cubic centimeter. That's right. You want to go to cubic centimeter. Centimeter is a factor of 10 to the 2. Cubed is 10 to the 6. Lower that by 10 to the 6, you get 10 to the 3. That's 2 times 10 to the 3 kilograms per cubic centimeter. So cubic centimeter is, again, smaller than the, it's a dot, it's a plain dice, right? It's a teaspoonful. A teaspoonful of this stuff is 2 metric tons of material. Right? All right, what is the surface gravity on this thing? Let's do it on Morpho Math again. G is, you know the surface gravity? I'd have to look this up, so I wouldn't click on that. It's GM over R squared. That's the acceleration due to gravity on the surface of an object. G times the mass of that object divided by its radius squared. So let's do gravitational constant. Could you stand up on this thing? That's the question. Gravitational constant times mass of sun divided by radius of Earth, quantity squared. Right? .2 times 10 to the 6 meters per second squared. That's 300,000 Gs.
Yeah, no, I don't think we can stand.
Don't count yourself out, Liam. I'm counting on you. You can do it. 3.2 times 10 to the, what did I say, 6 meters per second. Yeah. This is, about 300,000 Earth gravities. That's impressive. No, you're gonna be in trouble. The 27,000 K is gonna do it to you too. The G's gonna get you. The G's gonna get you. All right, where was I? And the spectrum bears this out. Oh, I don't even have. I think I showed you at one point. I should bring it back now. The spectrum of these objects, I've shown them to you already, and the pressure broadening on the surfaces of these objects is just tremendous, right? You have nice narrow lines on the main sequence and the giant branch, and you go down towards the bottom of the main sequence where the surface gravity is so high, and the lines just get broadened out to crazy widths because there's so much pressure broadening. There's so much jostling of the elements and jostling of the energy levels because of the high pressure that everything gets brought down. So spectrum bears this out. Very broad hydrogen lines and not much else. And in fact, Sirius B has nothing else. So people did this calculation. It's a pretty simple calculation to do, but astronomers at the time, many of them were like, that can't be right. This is crazy. No object could possibly exist that looks like this. And yet the calculations are so simple and the observations are so clear and obvious. It has to be right. And so, of course, we know that these today are white dwarfs. Okay, so what do white dwarfs look like? And how do we classify them? Where are my white dwarf slides? I had some white dwarf slides. Sorry? Yes, they are. What happened to my, I thought I had some nice spectra here of white dwarfs. Oh, here we are. Oh, we already did this. No, this is the supernova. Oh well. Maybe I think I should put it. Okay, so, am I out of time? I'm out of time. Oh, great. All right, we'll talk about properties of white dwarfs on Monday. Well, with this, it's going to be it's going to be more boring than you think. I'm going to go through the official classifications of white dwarfs and what this signifies the various classification systems of white dwarfs and how we actually go about measuring them. And then we're going to get into the physics of degenerate matter and how they're put together. Yeah.
Surprised that the white dwarf sector has very strong hydrogen bonds. Because that's
Right, because aren't they mostly made of carbon?
core,
Yeah.
which, like,
So there's different kinds of white dwarfs. The DAs are only hydrogen lines, the DBs are only helium lines, and the DC is no lines at all. And the DQ has carbon lines and some have metal lines. So it just happens to be what's on the physical surface. What survived.
So if there's still like hydrogen around the core, it does
Exactly.
get pushed off with everything.
Exactly.
Okay.
Or if some more hydrogen has fallen onto it in the meantime. So,
Okay.
and I think that's what's happened with Sirius. It's dumped some, Sirius has probably dumped some hydrogen back onto the surface of Sirius.
So, okay, so is there any way to look at a white dwarf and be able to tell what kind of star it was?